Good morning, early birds.
Good morning, Dr. Terrell. Do you get extra credit?
Yes, you do.
Oh,
Yes, perfect.
perfect.
Many extra credits in heaven. But unfortunately, this isn't heaven. No, I'm sorry. I give you credit. I like you, and whatever that matters. Yay. Let's see. Okay, I'm just going to be sort of getting ready here. So I'm not going to share anything. Just flicking around here.
Dr. Terrell.
So, yeah.
It's saying that you're recording right now, even though you're not teaching anything.
Oh my God.
Just letting you know. So the recording.
Thank you. Thank you.
Okay. And
I'm recording. There it is. There it is. There we go. Yay. Okay. So, a lab technician was asked to determine the weight percent of iron in an ore sample. Following results were obtained from 6 analyses. What degrees of freedom are in this data set? Well, the degrees of freedom for a straight average like that is very simple. It's n minus 1. N minus 1 equals 5. There we go. All right. A lab technician determines if the concentration of calcium in milk using 2 instrumental methods. Determines the concentration of calcium in milk using 2 instrumental methods. If calculated is greater than F table for the 2 sets of calcium data, what conclusions can the clinician make? Well, you remember that F cal is equal to S2 over S1 quantity squared, right? Oops. Right? And so that's the ratio of the standard deviations, right? And the ratio of the standard deviations is large if the if the ratio is large, F cal is large. If F cal is large, then the data must be different. So so A can be true, B must be true here, right? We look at the other ones. Difference is not significant, that can't be true. And that the data do not come from populations with the same standard. These are the correct answers here. An ore sample was analyzed for its iron content. Student A analyzed sample total of 6 times. Her result had standard deviation of 1.33. Same sample was analyzed 5 times by student B. His results had standard deviation of 3.42. Sloppy boys. To determine if their standard deviations are similar, they perform an F test. Calculated F value is going to be 3.42 divided by 1.33 squared. And the table value of F is, well, the tabulated value is F. You got to consult table 4.3, and I'm going to change my share real quick to table 4.3 here. And 4.3, we have to come down to, oops, sorry. We have to know the degrees of freedom in each data set. Let's see here. Student A analyzed 6 times. Student B analyzed 5 times. So there's 5 and 4 degrees of freedom, right? And so the 5, 4 value of F is going to be 9.36. And so let's go back to this guy. 9.36 F cal is 9.36, right? So we just have to compare these values. And if, I'm sorry, this is F table. Is 9.36, and then this is F cal. Right, and you just compare these values. If F cal is larger than F table, then the difference is significant. If not, then not. Okay. Oops, this is the same question. Honey. Bink. Okay. Students T is statistical tool used most frequently to express confidence intervals. Yes. That is true. Compare results from different experiments. That is true. Evaluate the probability of an experimental value agreeing with a known value. That's true. Determine if a questionable data point should be discarded. This is not true. So the answers here are these guys. And I've just got to, let's see here. Just got to highlight them somehow here. There we go. So let me see if I can cross this guy out. No, I don't have that here. Okay. So which statement regarding confidence intervals is true? As a percentage confidence increases, confidence interval range decreases. So increasing percent confidence, like 99, but so like as we go from like 80 to 90 to 95 to 99, that's our percent confidence. And as that value increases, then the range over which you can state that increases, right? So this is not true. The confidence intervals are calculated using the calculated mean and standard deviations of n and the result of the F test. No, you don't use the F test to make a confidence interval. So that's not true. The 95% confidence interval would include the true population mean in 95% of the sets of n measurements. Well, in theory, this is true. In theory, this is true. In practice, it's not always true. Okay. So this is not true. And this is not true. Okay. So the density of a solution is measured 6 times with the following results. Calculate the 95% confidence interval. Just know how to do this, you know. And then when you get your t value, you take the CI, and that's going to be equal to t times s over square root of n, right? And t is from the table. And which t would we use here? Well, we've got 1, 2, 3, 4, 5, 6. And we're using 95% confidence. So let's go to the, let's go to the, let's see here, new share, da-da, da-da, there we go. We can go to the student's t table here, and we can say, let's see, hold on, how many measurements do we have? We got 1, 2, 3, 4, 5. We've got 6 measurements. So that means we have 5 degrees of freedom. We're going to go for 95% confidence. So our critical value of t is 2.571, right? 2. Oh, geez. Hold on just a second. I've got something stuck in my keyboard.
Dr. Terrell, you're on mute again.
Thank you. Thank you so much.
Can you explain that again, please?
Yes, I got a crumb in my keyboard on the period, which is very useful. I'm sorry. So this problem here is basically you just got 5 values, right? And you can calculate the 95% confidence interval. It's basically X bar or X average, right? And then plus and minus TS over square root, and T is from table 2. And from that table, right, and I'll obviously have to give you the table, right? The value is 2.571. So this is basically what you have to do. I mean, just be able to do it's so trivial. I mean, it's just, you know, take the square root of n. N here is 6, right? N equals 6, and T 5 DOF, you know, from table 2. You know, the only other important thing is it's 95%, and you just look at that corresponding value in the table. Good. Okay.
Dr. Terrell, is S standard deviation?
Yes. Yes. S is standard E. Yep.
So would we have to do that by hand on the exam, or?
No calculating standard eaves, no calculating averages.
So we just give it to you in terms of S?
Yeah, unless I give you S and X average, right? So I'll probably just give you the average of the standard deviation. I don't need you guys freaking recalculate that for the 50 billionth time. Nobody does it by hand anymore anyway, so no one cares. Why does it take a long time to save stuff now? It's so strange. Okay.
Professor.
Yes.
Since we're going to have a lockdown browser, are we going to have access to these tables?
Yes.
Okay.
Yes. Yes. So I'm currently having a mental breakdown / crisis about the idea of doing the lockdown browser versus just like publishing something and having you guys like take pictures of it back in. I'm just not even sure what to do. But right now the plan is lockdown browser. So
Okay.
you know, I'm totally open for input. You know, if anybody's like violently opposed to lockdown browsing, then I'll probably change. You know, I just, you know, I don't know I've never done this, you know, this whole stupid online thing, you know, so I don't really know what to do.
Good question.
Yes.
Could we rather have like a take-home exam and turn it on Tuesday, because it was going to be on Thursday, and then have it on Tuesday instead of using lockdown browser, so you have the weekend to work on it?
No, not going to do that.
Okay. All right. Just
All right.
That's all.
Yeah, I know it's a good thought. I'd love it if we could do it, but it's just basically saying, hey, let's everybody cheat on this, you know.
Oh, I see. Okay.
You know,
I
it's
didn't
like,
think about that. My
what
bad.
can I do, you know? I mean,
Yeah.
I've done a ton of homework. You've done a ton of homework. I value that so much, right?
Yeah.
So I'm going to count it, right? But the exams have to be individual efforts. And that's what I'm going for here. That's what I'm going for.
I see. Okay.
You know, I mean, yeah. So I don't know. You know, I could make them all unique or something, but that's a ton of work. It's like, wow, you know.
Or what you were saying about having us just like work it out at home and then submit photos or, you know, scan it in, whatever. That way we could show our work and you could see that we're doing. I mean,
Right.
if we're doing the same problems, it's not going to look identical unless we are copying.
Right. I like that a lot. I do like that a lot. I just don't know whether it's an imposition. I just don't know about the scanning part, or taking pictures part. Maybe it's easy,
It's easy. I would allow maybe like an extra 5 or 10 minutes. It usually takes a couple minutes, and then just in case someone runs into something glitchy, but
Yeah. Alrighty, that's a good idea. That's a good
thought.
idea. Yeah, that's a good idea. I like that.
Dr. Terrell, can you clarify that formula in number 10 again for the confidence interval?
Oh, sure. So here, the CI is equal to X average plus minus TS over square root of n. So the CI is a range, right? It's X average plus TS over root n and X average minus TS over root n, right? Does that make sense? So do you want me to do it? I mean, I don't want to do it.
No, you don't have to. I just was the plus slash minus kind of got me lost a little bit.
Oh yeah. It's it's a range. Like the lower range of the CI is going to be they're all just the range around the average. It's going to range from X average minus TS over root n to X average plus TS over root n. That's really all it is.
Okay, thank you.
Cool. Excelente. Okay. The null hypothesis for comparing two means using a t-test. I believe, oops, what the hell? I believe the null hypothesis is that there is no difference between the true means of the populations that gave us the two averages above. So basically, this is the same number and it looks different because it's a slightly different value. But it's really, if you really measure it, the more you measure it, the closer the values will come together, basically. Okay. So how can we pick this out of this the two sets come from populations with the same standard deviations? That's not true because they could still be different. Different populations means isn't true. Two sets of measurements come from populations with the same mean and standard deviation. And I believe the answer here is E. So that would be a way to select that from a bunch. Because the difference, the T calculated, it's equal to X bar minus mu, right? It's that absolute value, right? And that's times square root of n over s, right? So So that's basically my answer there. All right. So a biosensor was developed to measure the concentration of aqueous arsenic. To determine the accuracy of the sensor, the sensor was tested against a standard reference solution of known concentration, right? The concentration is measured by the biosensor can be considered accurate if the known concentration of the reference solution falls outside. No, this would be bad. The accepted known concentration falls within. Yes, this is good. The standard deviations for the concentration determined by the biosensor and the accepted known concentration of the reference are not significantly different. That's not about the accuracy. Right? The standard deviations for the concentrations they're not significantly different. Well, this doesn't make any sense at all because you would use F to compare the standard deviations, right? So this is a WTF answer here. And then, so the answer here has got to be B. Because these are both WTFs because the T values do not compare standard deviations. So, method of least squares. The least squares draws the best straight line through data points. Yes, check. The equation for a straight line is y equals bx plus m. Not check. Or the m is the slope. That's the intercept as it's written. So that's a plant. Deviations in y are minimized because uncertainty in y is assumed to be greater than certainty in x. Yes, this is true. Actually, I rarely emphasize this, but you know, this is, you always calculate uncertainty as a function of y. The slope and y-intercept are calculated using determinants. They're not using calculated, using determinants anymore. So I would say 1 and 3 here. I mean, yeah, maybe 4, but 1 and 3. These are the correct answers. I would not give you this determinants thing because I didn't test you on that. Which term is incorrectly defined? Oh, geez. Linear range. Yeah, that's true. Correction absorbance. That's true. Blank. A solution containing all reagents and solvents used in the analysis to which no analyte is deliberately added. This would be a method blank. Standard solutions. Let me put method here. Standard solutions. This is not true. It keeps there. They do this stupid trick where they replace mean and standard deviation for mean, and so this is the false guy right here. I guess you could define dynamic range this way. Yeah, that's fine. So this answer is D. The absorbance for a dye sample of unknown concentration is measured. The corrected absorbance is 0.5482. The 0.5482. Do you want the concentration? You say you want X equals Y minus B over M, right? So you just substitute the Y value in. Oops. So we've got Y is 0.5482 minus B, which is 0.9, 0.0939. Hold on, I missed my equals here. And divide that by 696. There we go. That's how you calculate that. Not too big a mystery. For a Gaussian distribution, the average percent purity for a batch of acetic acid manufactured by the Acetic Acid Corporation is 97.5%, with a standard deviation of 0.2%. The minimum percent purity a buyer requires is 97.0. What percentage of batches will have a purity unacceptable to the customer? This is a good question. So what you need to do is redefine this value in terms of Z. So let's do this. So let's say 97.5 is equal to mu, and 0.2 is equal to sigma. Then the value, the 97% value, corresponds to let's see, 97.5 minus 97 divided by 0.2 is equal to Z, and this is the minimum percent purity, right? And what we want to know is what fraction of a Gaussian curve lies within or lies below, rather, Z equals this value, right? So 0.5 divided by 0.2 is 2.5. So what we can do or we could say what lies above Z equals minus 2.5. That's maybe a better way to put this, right? And so we would have to go to the table, the Z table, and then find 2.5 or minus 2.5 and see what makes sense. So let's see if we can do that. Actually, I'm pulling up the students' T table here. Or the Z table rather. Okay, coordinate an area for the normal error curve. Yeah, that's where it is. Well, I'm going to leave it here, guys, because I don't have access to that table right
I can find it.
now. Okay. Oh, I found it. I found it. There we go. So here's the normal error curve, right? And the thing about this is symmetric. And what we want is 2.5, right? We're going to say, well, there's we're going to look at the area corresponding to 2.5. And that area is 0.4938, and this maxes at 0.5, right? So let me go to the document camera here. So I'm just going to jot down the value. And with the Lushar, which is document camera. Oops. There we go. So, sorry, this is kind of weird looking here, but the idea is that we've got 0.493 of the area of the curve is corresponds to this value of z equals 2.5, right? And so let's just look at this value one more time. Right. So what this is saying is that for a Gaussian curve, right? If we just consider this half of it, the z equals 2.5 value is somewhere out here. And of this, we have already covered approximately 0.4938 of 0.500, right? So there's also a wing out here, which if we're considering only the cases that are out here. Then we can say that we've got 0.5 over here plus 0.4938. And this is, 0.9938. Oops. So we've got only about 0.2, maybe 7 there. 0.0072% of cases, oops, 0.0072, which is equal to 0.72% of cases will fail. Does that make sense? I got this subtraction wrong, but it's just the difference there.
Yeah, kind of. I'm just following along.
Yeah.
To be honest.
Yeah. So hold on. Let's look back at the
True. Would we expect this type of problem on the the midterm?
This would be a hard one, but this is, I mean, maybe one, maybe not. Maybe one, maybe not, right? So hold on. Let me go back to the problem. Got to get more agile with these to share things. Oops. Yeah, there we go. So the thing is that, they're 97.5 plus or minus 0.2, right? This is really tight. And so what they're really asking is what falls below 97, right? And that Z value is minus 2.5, right? Because this is so small, the 0.5 divided by 0.2 is 2.5, right? So that's a large deviation given what they've stated, right? And then you can use this table to draw the curve and see how much area lies outside of that Z equals 2.5 value. So I know it's kind of a stupid mental gymnastic exercise, but you've seen it done, right? You've seen it done once, and you probably won't have to do it. And I'll tell you what, if I give you this, I'll package it more nicely. But no guarantees, but I may not give it.
So, Dr. Terrell.
Yes, Brandon.
Dr. Terrell.
Yeah. Oh, yes.
So if we had this kind of question on a quiz, would we only be looking at one end of the Gaussian curve, since I'm sure they wouldn't be unhappy with a higher purity?
Right, exactly right. And the purity here can go to like 200%, It's like, what? That doesn't even mean anything, So I'm just ignoring all those possibilities. So like it would basically be, purity can go down to 0%, right? But it can't go above 100, right? So it's just sort of like a goofy thing here. Okay, so moving on now. Let's see here. 60. Yeah, I got yeah, I got 0.493. They got 0.62, I got 0.72. So anyway. So So here, let's try this one. A researcher developed, I think this one's 26, developed a new analytical method to determine the percent by mass iron in solids. To test the new method, the researcher purchases a standard reference material that's 2.85% iron by mass. Analysis of the iron standard with a new method returns values of blah, blah, blah. Does the new method produce a result that is significantly different from the standard value at 95% confidence? Okay, so what you want to do is you want to create a T calculated, right? T cal equals x minus mu times square root of n divided by s, right? So,
Are you typing this in, Dr. Terrell? I don't think we can see it.
oh, you can't see it? That's weird. Because my, yeah,
I could see it.
you can see it. Okay, maybe I'll make it a little.
Oh, if you see anything in the chat, open the chat box and close it again because the bar across the bottom may be covering it.
Oh, thank you.
Yeah, I'm trying to hear it. Let me make a. Oops. Let me make some space near the bottom. There we go. Hopefully this helps too. Okay. So T cal is x minus mu times square root of n over s, right? That's all you need here. And the question is, is T cal greater than T table? Right? This is the question. So mu, this is mu. So this is going to be like equal to it's basically x average, right? Minus mu. So you can calculate x average, right? Oops. And then mu here is 2.85%, right? So then times square root of n over s, right? Square root of 5 divided by s. I'm not going to calculate s. And then you just compare this to T table. Right? And if the T cal value is larger than T table, then there is a larger difference, then the method is inaccurate. Right?
So that means that the method produces statistically significant Or significantly different results then?
Yes, yep. It's kind of cool, right? Because basically what they're saying is that there's this universal distribution around T that it'll tell you whether a method is inaccurate, right? You just need to know the standard deviation. And you know, it always assumes that things are Gaussian, right? And it's kind of a crazy assumption sometimes, but it gives you a guideline, you know, it gives you something to go by. Don't take it like the holy gospel unless you know the thing is giving you a Gaussian response, right? Okie dokie. Let's move on here. Let's see here. Which statement is not true for light modeled as a wave? Right? So frequency is the number of oscillations that a wave makes each second. Yeah, that's true. Wavelength is the distance between the crest of one wave and the trough of the next. Not true. Sorry. It's between crest and crest, or trough and trough, or zero crossing and second zero crossing. So that's not true. Light travels slower through matter than through a vacuum. That's true. Speed of light in a vacuum is 2.98 1028. Last I checked, the product of the frequency and wavelength of light is the speed of light, and that is true in vacuum. But you know, light. You know how light bends when it goes into a medium? What changes, the frequency or the wavelength? Okay, so the answer here is B. Okay. Okay, if light is modeled as a particle, which of these is false? Particle light is a photon, that's true. Energy is proportional to the frequency, yep. Proportionality is Planck's constant. Wave number is inversely proportional to energy. Not true. Wave number is directly proportional to energy. That's false. Energy of a photon decreases as its wavelength increases. That's true. The product of H and nu is E. That's true. So here, the outlier is C. Okay. Here's a good one. No one will ever ask you this. What is the energy per unit time per unit area in a light beam? Radiance, absorbance, transmittance, molar absorptivity, or frequency? Well, that's easy because we're talking energy per unit area, right? So it's got to be a radiance here. Yeah. Okay, calculate the energy of a photon. This is like a stupid easy gimme question. I might throw one in. Oops. E equals H nu equals H C over lambda. Which of the following is not true about light absorption? Transmittance is the fraction of incident light that is not absorbed. That is totally true. When a molecule absorbs light, it is promoted to an excited state. Yeah, I guess so. A is minus log T. True. When a molecule emits light, it returns to a low energy state. True. And irradiance is the energy per second of a light beam. Well, irradiance is energy per second per unit area. So here's a stupid ass, chintzy, cheap, stupid question, which I probably will never not ask. Because it's just like, do you know that irradiance is energy per unit time and area? Stupid. Anyway. If 90% of light is absorbed, and according to the following equation, oops. Sorry, didn't get copied that. 99% of light is absorbed, and according to the equation here, what is the absorbance? Log of 0.99. The log of 0.99 is, I'm sorry, the 99% is absorbed, therefore, %1 is transmitted. Therefore, we're looking at the log of 0.01, right? Which equals minus 2. Oops, minus 2. Forget the 3, 2. I said 2, right? So because basically, if this were this would be -1, right? And then if log of 0 is what is, wait, no, I can't do log of 0. Log of 1 is 0. 0. And then, so 0.01 is -2. Therefore, A is equal to 2. Okay. Alrighty. Which Beer-Lambert statement is correct? Absorbance increases as concentration increases. Yes. Absorbance decreases as path length increases. No. Crazy people. Molar absorptivity value is chromophore and wavelength specific. And that is true. Let's see here. Let's get the next one. The absorption spectrum is a graph showing how absorbance changes with wavelength. Yes, that is true. Okay, so this guy is, that is the outlier there. Okay. So here's the data we have. 3.7 times 10 minus 4 mole of solution. Compound X has an absorbance of 0.5342, measured at 740. Assuming a path length of 1, calculate the molar absorptivity of the compound. So the molar absorptivity is what we're wanting here, right? So absorptivity is epsilon, and it has units of molar and centimeter per molar centimeter, per molar per centimeter, right? Right. And that is, this is going to be, and we know that epsilon times B times C is equal to A, right? So, what do we know here? We know C. We know A. And we know B. So, let us calculate. So, EPS then will equal A over B C, right? Will equal 0.532 or 5342 divided by 1 times 3.70 times 10 minus 4. Oops. So, quick question for everybody. How is my audio right now? Because I listened to the last week's thing and audio was horrifyingly bad. And I'm just asking, is there a lot of background noise in my audio right now?
It actually sounded fine today.
Yeah,
Good.
I think it's fine.
I think it's okay. We can hear you.
Oh, good, excellent.
It's good today, yeah.
Dude,
Thankfully, it's good today. Yeah.
yeah, I'm using my old computer here, so everything's better. You know, it's like a 10-year-old Lenovo. It's like, yay, everything works. You know, the expensive Dell computer I bought, like, no, doesn't work. Too many fancy toys on there. Okay. All right. So let's keep going here. So, about this one. So, which of these is not one of the 4 components of the basic spectrophotometer? Sample cell, monochromator, beam splitter, light source, light detector. Well, basically, you don't need a beam splitter. This is just not part of a spectrophotometer. You need a source, monochromator, a cell, and a detector. So anyway, that's simple enough. Here's a good one. What material should be used for a cuvette if a technician or anybody needs to measure a sample that absorbs at 255 nanometers in the UV region, right? The answer is basically quartz or fused silica. And so that's the answer there. It's not KBr, not glass, because glass absorbs at 255, not polystyrene, you know. So there you go. Here's a good blast from the past. Reagent blanks are primarily used to align the optics, compensate for absorbance, verify reagent purity, calibrate spectrophotometer, test detector sensitivity. Really, the only function of a reagent blank is to compensate for absorbance due to reagents and/or contamination. You might have some idea if there's a terrible problem with purity, right? But this is not the primary use. Right? Let's do Beer's law here. Beer's law works for blank radiation passing through a blank solution in which the absorbance species is blank in a constant concentration dependent equilibrium. I don't know why that's snapping over there, right? So I would say the blank one is monochromatic because it modifies radiation, right? And then through a dilute solution, and then your analyte cannot be in a concentration dependent equilibrium, you know. So those are the answers there, you know. Okay. Let's do this guy. Let's do some descriptive photophysics here. Which statement about the excited and ground state of molecules is false? Okay. When a molecule absorbs light of sufficient energy, it is more likely to undergo S to T than S to S. So this is super easy, guys, because S to T is forbidden, right? So it's weak. So we already found one false one, right? Electron spins are parallel in triplet and opposes. That's true. internal conversion is non-radiative transition from S1 to S0. That is actually true. When a molecule absorbs light, hold on, of sufficient energy, electron transitions from S0 to S1 state. I disagree with this statement actually, in a super picky way, because the state of the molecule changes, but it's not. You can't blame it on a single electron. But okay, whatever. We'll just use this stupid, sloppy chemistry vernacular here. Intersystem crossing is a non-radiative transition from T to S. That is also true. So the only false guy here is A. All right. How about an easy one? The excited state in which electron spins are opposed is called the singlet speed. Now it's an excited state. It can't be the ground state. It can't be a triplet because spins are opposed. Phosphorescence and fluorescence are decay modes, so they are not descriptions of a state. Okay. Let's try this puppy dog here. Fluorescence is a non-radiative transition between states of the same spin. Yep. Non-radiative transitions between states with different spin. Technically, that's phosphorescence.
Wait, don't those release a photon when they relax?
Oh yeah, you're right. You're right. Exactly. So it's neither of these two. If these had read radiative, then that would be true. So fluorescence is a radiative process, right? Sorry about that. Thank you, Kareem.
No
So
worries.
there we go. I need a check now and then. Let's see here. So the emission of a photon during transition between states of the same spin, like S1 to S0, yes. And no, this is phosphorescence. And so the only one of these that's actually fully true is this guy, right? However, there's a weird distinction, right? Is how do we know if a state is a triplet? Well, we can measure it magnetically. We can split the state magnetically. So we can look at the Zeeman effect, basically. But if you don't know that a state is a triplet, then you can't really identify it as phosphorescence. But in practice, what is done is everything with a lifetime of greater than 10 microseconds is called phosphorescence. And it's most likely phosphorescence. But it's an older, somewhat sloppy form again. Okay. All righty. So, all righty. Okay, let's do emission excitation. We'll finish up with these. Oh, okay. Actually, I'm over time. Sorry, but I will give you guys the remainder of this. I'll just put the remainder of this thing on Canvas for you. Okie dokie.
Dr. T, for
Yes.
the exams, do we need lockdown browser monitor version or lockdown browser only? I just want to clarify.
Have the lockdown browser, but don't worry about Respondus.
Wait, that is the lockdown browser.
I'm
Wait, what?
sorry. Well, there's what were you asking, Fook? Sorry.
I'm not sure if anyone take the same class as me before, but I think there are two versions, if I remember correctly. Lockdown browser and lockdown browser monitor.
With or without camera?
Yeah,
Right. And I'm not going to use the camera. I'm not going to use the camera. So I may use the lockdown browser, but I will not use the camera. I just feel like that's so weirdly invasive. I can't even do it. So
Dr. T, would it be possible if you help us make a test where it's no points attached to it, and we can test to see if our version of lockdown browser works or not? It's
I see. Right.
Just a free test. No
Okay.
points attached.
Okay, I'll do that. I will do that. Oh.
Dr. Chow, one quick question.
Yes, sir.
So for Thursday, we just log into Canvas and take our exam through lockdown browser, correct? We don't need to go to the Zoom. Yeah.
Right. Correcto.
Okay, thank you.
Correcto mundo.
Professor,
Yes. Yes, sir.
did you say we were allowed a cheat sheet as well? Or no? Remember you mentioned it before.
Yeah, I don't see why not. I mean, it's like, you might as well make one. I mean, there's like, yeah, go ahead. I don't care. It's fine.
Okay, sounds good. Thank you.
Sure.
Dr. T, would there be an assignment where we can upload our work, or do you don't need for us to upload our work?
I'm definitely leaning towards letting you turn in your work. So
Thank you for that, Dr. T. That's very helpful.
Excellent.
It's
Oh,
a
good.
keyword.
Okay, good. I just don't even know. I've never done this, and it's so strange. But yeah. So I'll let you turn in your work. I will. I'll make another place, a place for you to turn in. Okay. All righty. It's sort of coming into focus. I'm really sorry that there's so much in my own mind about the exact format, but it will be a normal Canvas quiz, and there will be places to turn in your work. There will be a hand in your JPEG here type of thing. Okie doke.
Thank
You
you.
said that no Excel would be required, right? Oh, I'm sorry.
Right.
Someone
Yeah.
else
No
asking.
Excel. No Excel.
And
Exactly.
you said you're posting this entire document on Canvas, right?
So the Canvas quizzes, right? They just they're all pre-digested. They're all just like enter, select this. It's like a DMV thing, Does that make sense, Jordan?
Oh, I'm sorry. What I was asking was this review sheet. You're posting this on Canvas, right?
Yes. I'll post this on Canvas. Yes.
Okay, thank you.
All righty.
Wait, what do you mean that the exam is going to be like the DMV? Like
Yeah.
multiple choice?
Yes. What do you mean by that, Dr. T?
Well, it's like it's all online. It's like there's you may have to enter some numbers here and there, but it's like you enter a few numbers, you click a few boxes, whatever. I get to see everything, right? That's all I mean.
Dr. T, you will give us.
What?
You will give us the. Dr. T, will you give us the equation or the formula, or we do it ourselves?
You know, yes, I'll give you formulas. I will give you formulas.
Thank you.
Okie dokie.
Dr. T, will
Yes.
we see all of the question all at once, or do we see only one question at a time and then cannot go back to the previous questions? I just wanted to ask that question.
That's a good question.
We will be able, like we will be
Yeah,
able
right.
to check our answer, because I usually do one first.
What do you think, Casey?
I think I hate the questions where you can't go back and check because it's not what a real test is like.
Okay. Okay. So we'll let you go back and check your answers.
Okay,
Will-
thank you.
Will we
I don't-
see all questions at once, like the normal test, Dr. T? Normal physical test?
As much as possible, I'll make it like a normal physical test. Yes.
Okay, thank you.
All righty. Okay, kids.
Thank you so much, Professor, for doing all this to make our test as good as it can be. I know it's a lot of work.
Thank you. Thank you. Thank you. Yes.
I appreciate it, Dr. Terrell, because
Yes.
life
Well,
is crazy. So
life is
appreciate
crazy.
it.
Thank you. Thank you, guys. Okay.
I
Cool.
really do.
Thank you, Dr. T.
Wow. Oh,
Thanks,
man.
Dr. Terrell.
Oh, come on. Come on.
Have fun.
Stop it.
Thank you, Dr. T.
Thank you,
Bye.
Dr. T.
You deserve it. You're a fun teacher, unlike
Oh,
some
no.
people. So
No.
you deserve the
Under my
praise.
hand.
We're not hyping up for nothing, because we don't say thank you to teachers, because teachers are not fun. But thank you for your time, and
Okay.
I will see you.
Okay.
Solomon
next
just
chapter.
wants you to drink with us, that's all.
Bye. Bye.